Welcome back. Now we'll look at some of the examples of how high-performance computing architecture and memory get implemented when computers are made. After that, we'll look at some examples of how you use it, which is easy. So now we'll look at some of the detailed examples, and it'll help make some of the concepts clearer. So let's look at the next slide. Now this is good. We've spoken in broad generalities, given you some details, and now we'll look at one specific case. So we'll look at an example. And I think what we've seen before will begin to make sense after this example. And certainly you're welcome to go back on the slides here and look at these examples again as we use these words again, because there's a lot of new words which have come rather quickly. So here on the right we have this very nice picture, and it's not a real picture. In fact, it's one you've seen already, so that's good. We'll review it again. And this is a model of the central processing unit. So you can think of this flowing like a waterfall. Here's main, hard disk, the data is going through RAM and swap space into RAM, flowing through the data cache into the CPU. And so the model, if you want the insight into how the central processing unit works, is it works via interacting memories. There's different levels and hierarchies of memory, and they all interact with each other. And you have to program for that in some way. So here we have a pipeline. And pipelines are important to get speed in the processing. Pipelines are like bucket brigades in a fire. The old, before they had fire engines that would do it all, they'd have a village pump down in the main square with lots of buckets, and you have a lot of people in line, one feeding a bucket to the other, and the guy at the end would throw the bucket on the fire, pass the empty bucket down the other line, and it would keep going the whole time. And there'd be water coming even before it was used, and it was planning ahead. That is very much how this works. So here on a central processing unit of a computer, it works with pipelines, and these data caches are the pipelines. Okay? And as you can see, the data caches have multiple lines in them, and they have multiple stages which can move data from one stage to the other in different places, and you can have different pieces of data in different parts of the cache. So you have to program for this, but it can do quite a bit of pre-processing, so that even though the instruction you're operating on at one time will only be one instruction at a time, the processor doesn't have to wait for a data element. They should be right there at the top of cache to take it off. So let's look at an example. Let's say we have a very simple example. We want C, a number, to be A plus B divided by D times F. If we look at this equation, we could say, well, the computer can figure out what to do at each stage. But the compiler, your Fortran, Java, C compiler, could say, I know I need A plus B, and then I'm going to do D times F. Well, I better be ready with D times F when A plus B is already computed, otherwise I have to wait to fetch them. So it's done in stages. So the one unit, let's say unit A1 on the central processing unit, in the first step will fetch A, and then in the second step we'll fetch B, and then in the third step we'll do what? We'll add them together. But simultaneously with that, unit A2 can be, so another cache unit, okay, can be fetching D, and then the next step be fetching F, and then in the third step can be multiplying them together. And when I say step here, what do I mean? Well, step is related to the clock cycle. You always hear the CPU quoted in some time, so many, megahertz, which means millions of cycles per second. So each step is at best one cycle. Sometimes it may take 2 cycles, depending on the hardware and the software. Okay? But you can think of it, each cycle, one step, something gets done. And finally then, the last step done, the real answer, you divide A plus B divided by D plus C in another unit. Okay? So this information gets transferred then as little as possible. It's ready for use as much as possible. So now let's talk about just words again. Here on the right is the same diagram you've seen on its side, so the data is spilling down to the bottom. Let's talk about CPU design. So you don't have to do this yourself, but the words are used all the time, so it's important. So in particular, RISC. RISC is used all the time, Reduced Instruction Set Computer. That's what it stands for. This was revolutionary in its time. In the early 1980s, this led to inexpensive computers, desktop computers, which would rival supercomputers. So it was a revolutionary change. To understand what RISC is about, and I think it was Seymour Cray who designed the first RISC's ideas, you should understand what was the prevalent type of supercomputer, high-performance computer design at the time, and that was called CISC, which is Complex Instruction Set Computer. So the difference was that previously on the chip, on the actual central processing unit electronics, there'd be high-level code. This would be like Fortran or Java, right on the code right there. Not quite that sophisticated, but there might be thousands of instructions that the central processing unit could follow, and these were complex high-level instructions. And when I say complex high-level instructions, I mean an instruction like you might give in Fortran or Java, where you say C equals A plus B. A low-level instruction would be something you shouldn't have to ever do it, but you know, if you're programmed in basic machine language, where you'd say, oh, I have to fetch A from its memory location, move it into this data register, fetch B, move it here, then, you know, combine these two memory location values, move it there. Those are low-level instructions. So this CISC, the previous architecture, would have high-level instructions, but the price you paid for that was that they were slow. You know, it might take 10 TOR, 10 machine cycles to execute each instruction. Okay? And there had to be lots of instructions. So RISC was a philosophy, was a bright idea, and said, why don't we instead make the central processor unit much simpler? Make it smaller and only let it have a small number of instructions that it can follow. And then we rely on compilers, the Fortran, the C compiler, to be very smart and figure out how to make best use of these instructions for itself. Okay? And by having that, then the amount of time any one instruction would take would be smaller. Okay? So fewer cycles would needed to get through the instructions. It would be cheaper to actually produce these chips, which is what made them revolutionary, that everybody could have a high-performance computer. And possibly, if you did all this right, you'd even end up with a faster computer. So that was surprising. One reason it was faster, and this is where it comes down to what you and I just talked about, is by having a smaller number of instructions being saved on the computer, you have freed up space on the chip, in the actual silicon, as they say, and then you can have more CPU registers, more cache on the chip. So you can actually speed things up, have larger cache, more buffer, have information available more of the time, and help speed up the calculation. So this increased the number of pipelines. It decreased the number of memory conflicts. In other words, that was when you'd need to do something in the central processing unit and it needed a piece of data which already was being asked for someplace else. You had to wait for it to free up. Here you could plan ahead better with more cache, and permitted you to do some parallel computing as well in the cache on the CPUs. Okay. So if you want, the mathematical theory behind this all is that if we ask, how long does it take to do anything on a computer? Very basic question, and has a very simple answer. Well, the amount of CPU time it takes is just equal to the number of instructions that you have to execute in your program, let's say, how many cycles it takes for each instruction, whether it's RISC, which is very few cycles, or CISC, which is many cycles, okay, and then the cycle time of the computer. So when you buy the world's fastest computer, what you're buying on the marketplace is just, you get a very fast cycle time. But they don't tell you that. Maybe a very fast clock cycle, but you may need many, many cycles to get any one instruction done. Okay. So the CISC point of view is you have fewer instructions executed, so you don't have that many instructions to execute, and that should, in a linear relation here, it'll speed up the processor by having fewer instructions. That's true. RISC says, aha, by having fewer cycles per instruction, I can also speed it up. So obviously, and you're not going to change the hardware, or they both change the hardware. So obviously, in order for RISC to give you a faster speed up overall, even though you have more instructions, the speed up you get from the having fewer cycles per instruction must overweigh the other. And by and large, it's true. It's worked that way. Okay. So now, let's take a break. Now let's look at fun. Okay, let's see what have people done? What have the manufacturers done? So look at slide 9. Look at this beautiful picture. So this beautiful picture is IBM's latest and greatest supercomputer. It's called Blue Gene, and that's not because they want to look like a bunch of hippies. It's called Blue Gene because Blue is IBM, and it was originally derived and developed for work in biology, gene sequencing, as a sort of a special purpose computer, and then with a few tweaks here and there, they brought it out as a general purpose supercomputer, and it does very well. At least as of recently, it was the world's most powerful, fastest computer. Whew. And we'll talk about the individual pieces, and don't let yourself get buried in the details. Try to keep your head above water and think, how do they assemble this computer? How is it done? Okay. Well, the answer to that, and maybe it's sort of typical for IBM, is the answer is it's a computer designed by committee. No one part of it is wonderful and great, and the whole thing is integrated together with lots of worries about lots of details, but not with one consistent vision throughout. Okay, so it's not like the Cray supercomputers, which used to do that, but they couldn't make it economically. This could make it economically. Okay, so it's a balance. The whole thing is a compromise. It's a compromise on the one hand here between cost and performance. They could make a faster computer, but it would cost a lot more. So they're trying to keep the cost down by using components that are essentially off the shelf, very few designed just for this purpose, but they work for other things as well. And then also they want to balance that with, they can increase the performance on these machines easily just by making them run faster, but that makes them hotter. And that's good for the environment. You don't use as many watts for electricity, but it also means if it runs hotter, you have other overhead worries to concern yourself with. Essentially, you damage the equipment, it becomes unreliable, tends to melt. So heat is the element now that is keeping supercomputers more than anything else from getting faster. So probably a whole new technology will be needed to generate supercomputers of the future, because you just can't keep making them faster and faster, because that makes them hotter and hotter. Okay, so now this is built up step by step, little pieces to bigger pieces, almost with no end in sight. The basic chip, in other words, the basic, piece of silicon that has electronics on it, has 2 central processing units. So it's a 2-chip processor. Each processor runs at 2.8 gigaflops. Okay, so a flop, remember, is just a floating point operation, which is good. It's not a cycle time, which doesn't mean very much, because what really matters is how long it takes to do a floating point operation and add or multiply with floating point numbers, because that's what scientists use. So this can do 2.8 jillion of them, 10 to the 9th. Okay, so that's a lot. Okay, and on the chip itself, there's 4 megabytes of memory, which is a good amount of memory. Okay, the next, so these are the cores. The next bit up in complexity here is that a card is made. The card fits into a circuit board. Okay, so and the card has 2 chips on it. So that just doubles all the numbers, and then gives you a total of, on the card, 11 gigaflops of processing. So it's just twice what a chip had, and the chip has 2 processors, okay? And it also has a gigabyte, which is a lot of memory to have just on the card, of DDR. And DDR is just its memory, and it stands for double data rate memory. And what it means is it's not only is it the amount of memory, but it's fast memory. It's very fast because you can transfer memory on each clock cycle, both as it's beginning the clock cycle and as it's ending the clock cycle. So sort of double speed memory on the card. So, you know, they try to make it fast, and then you integrate that together, and you say, once I have a card, I can put a bunch of these cards on a board. You can put how many of them on. You can put 16 cards in a board to give you 80 gigaflops. Okay, and I think you could probably buy the board, but the usual way is to say, okay, I can now buy a cabinet as a supercomputer, and the cabinet itself has 32 boards. So the cabinet gives me 5.7 teraflops. So that already puts you in the teraflop range of computers, which is tremendous. And then this thing scales incredibly high. You can put together 64 cabinets, all integrated, communicating with each other with the same architecture, working on the same problem, for a tremendous 360 teraflops and 32 terabytes of memory, which is a huge amount. But you see, it's not, you know, it's not one central core with one brain. The brains are right here if you want. It's just built up together. And as you can imagine, you know, this is extreme scale. There are 2 to the 16th when we're done nodes put together, so that's 65,000 computers, PCs type computers running together. The actual speed of any one computer is only 5.6 gigaflops. You may say, that's a lot faster than I have. Yeah, but it's not fast. You can buy a desktop computer at that speed or faster now, but they don't want it to be too fast, both because, number one, it would be hot. You have to keep it cool to keep melting. That's number one. And number two, remember what we said at the beginning of this discussion? We said you have to have a balance between all components. Well, there's no point in making a CPU tremendously fast when what you have to do is communicate between 65,000 computers. Okay, that's a lot of communication. That's slow. So there's no point in having the computer much faster than the communication time. Okay, so it's medium fast, and the control is done with a free, non-proprietary package with MPI. Okay, so that's message passing interface. We'll talk about that at some time soon. Not that soon. But that's how the communication goes. So it's not proprietary. You can afford it. It all works. So, but as we've seen, it's not so much the central processing now. When you put thousands and tens, 65,000 computers together, it's the communication that matters. So let's take a look now at slide 10, and we'll talk a little bit about how the communication goes. So the heart of the communication network is what's known as a three-dimensional torus. So this is in space in 3 dimensions, and a torus is like a donut. So it's a way of wrapping the wires together to connect all the different computers. So here in the diagram, we have a 2 by 2 by 2 dimension torus hooked together with the blue, red, and green wires, and that's the toroidal configuration. Okay, and that's the heart. So you have to imagine, okay, that's not so bad. Well, yes, but IBM did it now with 64 on one side, 32, and 32 on the other. So this is just a huge amount of wiring all hooked together this way. Each link, in other words, each part here, each link is made by a central processing unit. So remember we said on the previous slide that each chip has 2 central processing units. Now you see why. One of them is just dedicated to do number crunching. The other one takes care of the communications. And then if it has time, it helps with the number crunching as well. But communication has become such a key element in high-performance computing that as much computing power is used for communication as is used for number crunching. They have to be with this much communication. Okay. So the links here, the communication is both nearest neighbor, you know, just the guy next door, as well as a cut-through network so you can get to somebody in the next town, in the next cabinet, as it were, board, wherever. and it's designed as much as possible to have approximately the same effective bandwidth for all nodes. So bandwidth is just a commonly used term. It's the amount of data that you can send from one place to another. Typically, in a certain time interval, but a broad bandwidth means you can send, it's broad. You can send lots of information down the channel, okay? So they get node-to-node communication of about 1.44 gigabits per second, and so there's communication time of about a nanosecond, so that's very good. But that's good or bad, that's what it is. Okay. So the actual speed of the program you run depends somewhat on the local communication costs, how much it is, and how much, involve latency. So the latency here is either as small as 100 nanoseconds to as large as 6.4 micro, 10 to the minus 6 seconds. That's 10 to the minus 9th. So there's a factor of 10 to 100 here, and that's because if you have to communicate by 64 hops away, it could be as long as that, it takes longer. Okay? So that's the latency, adds to the latency, the time it takes to do something. Okay? So communication network is a whole separate network. So in order to have global communication on the broadband, in order to broadcast, in other words, say, everybody add element A you have to element B that you may have, and do it simultaneously, you need a special communication network. That network B here, and that's separate from the local network. And finally, how do you communicate with the rest of the world? How do you communicate with the hard disk? How do you print something out? How do you read your email? You don't read your email on these systems, okay? That's the control network, and that's a gigabit Ethernet. So it's fast Ethernet, but it's just proprietary commercial device, and that here, as you can see, with switches and so forth, communicates everything. It communicates with the outside world with the I/O. So you have 3 separate networks put together. It's not the most elegant, but it's powerful. It's how you get the job done. So now, let's look at the very heart of slide 11. And you'll enjoy this. So take a break. Think of what we've seen on the previous slides. Let's look at this. Why you should enjoy this, if all has gone well, and maybe if you've listened to this lecture now 2 or 3 times, is that we're going to show you the real guts of the world's fastest, most powerful computer, and you're going to understand pretty much what it's all about and why it works the way it does. That there's really no mystery on this thing. It makes sense. The numbers can change, but they're following the basic design. So here in our picture, we have the Blue Gene L. That's this model. ASCII was just the people who paid the money to have this developed. The federal government, the military, in fact. And there's 2 440 PowerPC cores. So this is an IBM proprietary processor, the PowerPC 440s. Who cares? Okay? But then it has 2 floating point units. So each processor has a special unit designed to handle floating point numbers well. So the floating point unit, remember the floating point numbers with the mantissa and the powers, they're meant for scientific processing. It's so important that it's built into the hardware right there. One of these is used for computing, the other is used for communication with the Ethernet. Okay. Each of these has a RISC. This is that reduced instruction set computer. RISC 7, so that's the level, 7 levels of CPUs with 3 pipelines. So what you're seeing here is, here's the CPU. But now we have, remember, these caches. And this is level 1 cache. We've talked about that. Then there's level 2 cache right over here. And then there's level 3 caches. So these are the caches. And the caches here is where the pipelines are. Okay? So we know what they do. That's how you can get information into the CPU as needed. Okay? The actual memory on this 2-core chip down here, the main storage, is 512 megabytes per node, which gives you a total of 32 megabytes. But this is the local storage, and if you need to communicate, you can get that much. The page sizes varies. Okay? So we know what pages are. We know it's how much memory is read in at one time into the RAM, and this is the dynamic RAM So it's that fast RAM, and it varies depending on where you are. And these are the 3 levels of caches we talked about. And you see them, they're different levels. They one directly feeds the CPU, the other feeds the pipelines, and the third is between feeds the RAM. And they have different sizes as needed. They get bigger in the places where needed, and this is how much information is in each. Okay, so how do we use this? I think we need to talk about that another time. It's actually not that hard to use because you won't have to do any low-level programming. We use this just with some general rules of thumb, and what we need to talk about is what those rules of thumb are. And now that you understand how the hardware is put together, you understand why we have those rules of thumb and what it's doing. So, we'll talk about that next time. Enjoy computing. Bye-bye.